In this module, we are going to look at passing traffic through the FortiGate unit and how that works. At the FortiGate unit's very core, it is a firewall, so everything that you do is built around the rules you create that allow traffic to move around. We'll be talking about how the FortiGate handles packets, different firewall policy types and subtypes, network address and port translation, session helpers, proxy versus flow-based inspection, firewall object usage, monitoring, and debugging of firewall policies, and other topics as well. By the end of this module, you should be able to properly identify the different components used in a firewall policy, create the objects necessary for a firewall policy, create address-based firewall policies, manage the order of firewall policies, test firewall policies, and monitor traffic through them. Firewall policies are really nothing more than a list of rules that define under what conditions traffic will be considered to match it. Assuming traffic does match the rule, the policy explains how to handle the traffic. Assuming traffic does match the rule, the policy explains how to handle the traffic. Should it be natted? Should it be logged? Should it be allowed or dropped? Should it be subjected to UTM inspection or not? Is there authentication that needs to happen, etc. You can see in this example screenshot there are several different firewall policies. If you take a close look at policy number 1, it will match all traffic that is trying to go through from LAN interface to DMZ. As a result, policies number 2 and 3 will never see any traffic because policy 1 is above them, matching everything. Now that we've covered some of the basics, let's talk a bit about what actually happens to a packet as it passes through a FortiGate. We will not be going into detail on each step. The first thing that happens is the packet connects to an ingress or incoming port. At that point, several checks kick in the following order. First of all, if you have a denial of service sensor in place, those rules come into effect. Assuming traffic is okay by that, the unit does an integrity check on the packet's header. Again, if that's good, we go on to the next check, which is to see if this packet is bound for a VPN on this interface. If not, then the next check is to see if there are any modifications that need to be done to the packet due to destination natting. After that is done, routing gets checked. After that, we get to step 2, which is the stateful inspection engine. The first thing to kick in here are the session helpers. We'll be talking a little later about what exactly those are. After that, the unit checks to see if this is management traffic for the unit itself. Next we move on to SSL VPN check, assuming that it has been enabled. Next comes user authentication, and then traffic shaping will kick in if there is any. Then we come to session tracking. Basically, if this is traffic that belongs to an existing session or not. Finally, assuming that no existing session was found in step 6, a policy lookup gets performed to see if the unit can find a firewall policy that matches this traffic. After the unit finds a policy for the traffic to flow through, the security profiles kick in. There are 2 steps to UTM scanning: flow-based and proxy-based. Some profiles have options for changing their mode. We'll talk more about the differences between flow and proxy-based inspection later. The order of inspection is important. Each of these steps happen in order, and the next step only happens if traffic is not blocked by the previous step in the process. After all this is the final step where the packet leaves out on the egress interface. That last few checks are to see if it belongs in a VPN tunnel, then any enabled source natting is performed. Finally, the packet is routed out the interface and leaves the FortiGate. When a packet arrives on an interface, the FortiGate unit analyzes it and checks its routing table in order to see where the packet should be sent. Assuming that it's a routable packet, it then looks at the firewall policies to see if there is a match. It examines the source and destination IPs, the port, and the time in order to find a policy match. Once a match is found, the rules on that policy are applied, such as authentication, UTM inspection, etc. The firewall policy sets up the rules for the traffic that passes through the FortiGate unit. Will it be AV scanned, NATed? All of these options can be enabled within the firewall policy. If you have no reason to allow the use of FTP, for example, simply block the port. Blocking or allowing traffic based on ports and IPs is your first line of defense when implementing security within your network. So your firewall policies need to be set up with care. Simply allowing users full access to all destination IPs and services, then relying only on UTM inspection for complete security, is like putting all your eggs into one basket. The best approach to sound security is to use a layered approach, and the first layer is made up of the firewall policies. The first question is pretty simple. A firewall policy for normal in and out traffic, or a VPN policy for a tunnel. VPN policies are discussed in other modules. In order for a VPN to work and pass traffic, you will need to create a VPN policy to allow users to connect and pass traffic. In this section, we will focus on the firewall type. So the next question is the subtype. Assuming you are making a firewall policy, the available options are address, user identity, and device identity. If you selected VPN, you would have different options which are covered in the IPsec and SSL modules. An address policy will identify traffic matches based on the IP address and subnet. This is your typical kind of policy that everyone is probably very familiar with, as every firewall supports those kind of policies. What is allowed or not allowed will depend almost entirely on your source or destination IP and subnet. A user identity policy makes its decisions based on user login information. Some kind of authentication to the FortiGate happens. This is covered more in another module. Device identity attempts to sort out what the hardware is and allows traffic based on the type of device being used. You can make a policy that applies to and provides different rules to iPods, Android, Mac PCs, etc. An address subtype has numerous options that you can configure for it. Initially, you have to consider the incoming and outgoing address and interface information. Where is it coming from, and where is it allowed to get to? After that, there is the time of day or schedule, then the service, also known as the port number. These initial settings are only to identify the traffic that will match this policy. After that, you look at options that will impact the traffic passing through the policy. Enabling NAT, doing traffic logging, enabling web caching, and WAN optimization. Finally, you have the option to enable various UTM security profiles like virus scanning and web filtering. Another kind of firewall policy is a user identity policy. Sometimes it's not enough to separate out your internal users based on their IP address. Perhaps, before being allowed to pass through the policy, they will be required to provide user credentials. These are then validated against local users, a directory server, an LDAP server, Radius, or TACAC Plus server. Authentication will be covered in more detail in the authentication module, but you can see here that at the top of the policy you have some of the same options of an address policy. However, in the middle is where all the real action takes place. who is allowed through and with what inspection rules on their traffic. A device identity policy looks similar to a user identity policy in a lot of ways. Within the policy itself, you set up the allowed destination addresses and inspection options for various types of devices. The way it works is the FortiGate identifies devices based on the packet behavior they exhibit. It looks at MAC address ranges, but only for Fortinet devices, since we know for sure what ranges our devices operate in. Not everyone publishes theirs, or if they do, many don't keep it up to date since there's no strong reason to. DHCP VCIs, so long as the FortiGate sees the DHCP traffic passing through it, the TCP SYN fingerprint, and HTTP user agent. The OS handles the detection with rules that are updated along with the normal FortiGuard definitions packages. If you are going to make use of this feature, make sure your device stays updated with a FortiGuard contract. Manufacturers are coming out with new devices all the time, so out-of-date definitions could lead to misidentification of devices. We'll cover this feature shortly. The first part of a policy includes the ingress and egress interfaces. The incoming and outgoing interfaces for the traffic. Traffic that hits this interface is allowed to leave out on another interface. Depending on the situation, this could be the same interface the packet arrived on. Interfaces can also be grouped into logical zones for easier configuration. This does not alter the behavior of packets, so it's not like link aggregation, it's simply a way of grouping together a couple of interfaces for easier configuration. In order to put interfaces into a zone in the first place, there needs to be nothing referencing them. So no firewall policies, VPNs, etc. Once the packet has arrived, has been considered valid, and has been checked against the routing table to find a destination interface, the source and destination IP addresses are then both evaluated. When you set up an address object, there is the default all object, but you can configure additional ones and use different types. Fully qualified domain names use DNS resolution to come up with the IPs of the host names entered. Geographic uses the units database to apply the subnets for the selected country, and ranges can be entered manually. The geographic address object database is also updated as needed through the FortiGuard updates. Finally, the ports and type of traffic are considered. A service can be defined as TCP, UDP, SCTP, or even a protocol number. TCP, UDP, and SCTP-based services have a source and destination port as well as a type of traffic. HTTP, for example, is TCP traffic with destination port 80. HTTPS is TCP port 443, and so on. It is important to note that it is the destination port because a service gives you the option to specify both the source and destination ports. Most software these days will hand off a packet to the operating system to deliver it somewhere with a destination port. The OS then opens a random source port to send the data. Only legacy applications transmit on a specific source port. Services are just ports and protocols that have been named to make them easier to reference. The next aspect to look at with a firewall policy is the schedule. This is really just the time. It's not uncommon to want some firewall policies that are only in effect at certain times of the day. To do that, you need to have a schedule that will match the time and day that you need. Most of the time, the schedules you need to make will be reoccurring, like a lunch hour for people at work. There is also the option to make a one-time schedule for something that will happen in the future. This might be useful for special events that don't happen on a regular basis. Now we're going to look at the concept of putting objects into groups. A group is just a collection of individual items that make it easier to configure rather than having to select each item individually, like putting a lot of groceries into a bag. Lots of different firewall elements can be put into groups, address objects, service objects, etc. This shows an example of putting together multiple services and grouping them into a single service group. These services would all need to be manually created by searching the web and finding what ports are used by World of Warcraft. You can set logging on an accept policy with one of three radio boxes. Log all sessions does not make a packet-for-packet copy of the traffic, but sends a summary of how much traffic was sent. For example, IP AAAA sent X number of bytes to IP BBBB on port Y. Depending on the amount of traffic that the policy is passing, this could result in a high volume of logs and impact available CPU resources. The exact behavior for these settings was already covered in the logging module. What is network address and port translation? When you send packets around the network, depending on the protocol, they have four pieces of information that determine the source and the destination. These are the source and destination IP addresses and the source and destination ports. The act of translation is when you change some of this information. Network address translation, or NAT, is when you change one of the IPs. It's not specific to the source or destination IP, but changing either of this is considered NATing. There are two subtypes of NAT which are specific, however. There are source NAT and destination NAT, and they are for when you need to be specific about whether you're changing the source or destination IP. There is also port translation, which is similar to the idea of NAT, however, you're only altering the source port of the packet. When you are surfing the internet, you are most likely doing so from a private IPv4 subnet. This same subnet is being used by millions of other people all around the world. Your IP needs to be changed in order for the packet to float over the internet and come back to you. NATing the traffic will change the source IP to match the IP of the interface the packet leaves from. It will also randomly shuffle the source port of the traffic at the same time by default. This is not always going to work. In some networks, you need to NAT the IP, but not use the outgoing interface IP. In this situation, you would create an IP pool and use that instead. This can be a range of one or more IPs. In this case, the unit remembers the source IP, so a given source will always use the same external IP from the pool of possible IPs. As with most NAT appliances, when traffic passes through the source port, it will also be randomized. This can cause issues with legacy software and other high security devices. Fixed port means that the unit will not randomly change the source port on the traffic. Generally, it is not necessary and is not recommended to enable this unless it is required. In which case, your best deployment would be to set up a specific policy for the traffic you want to apply this to and move it up to the beginning of your firewall policy list. There are 65,535 available ports for each individual IP address. Each port can only be used by a single session at any given time. So if there is a lot of traffic passing through a firewall policy with fixed port enabled, there is an increased chance that the port will not be available for communication. We have just covered source IP NATing for traffic passing through a firewall policy. But what about destination NATing? Let's say you had an internal web server and it hosts a website. It can get out to the internet on its own through a normal firewall policy just fine. However, in order for people to access it from the internet, it must have a public IP address for them to connect to. If you use NAT on an external to internal policy, you would only be changing the source IP. The destination address would still be a public IP, but the web server is internal. So what do you do? Well, you use a virtual IP to NAT the external IP destination through to the internal IP. There are two ways to set up a virtual IP. The first is to use a one-to-one static NAT. An external IP and all ports for that IP are specified. If you use this setup, outbound sessions originating from the internal IP are automatically NATed to the external virtual IP and not the physical interface IP. If you make a port forward virtual IP by specifying a port, then sessions originating from the internal device will only be NATed to your external interface if you have NAT enabled. In that case, you would need to use an IP pool to NAT the traffic to the virtual IP. Virtual IPs are needed when you have to change the packet's destination IP. Anytime you are initiating traffic that will go from a public network to a private network, you will need to use a virtual IP or VIP. Externally, the virtual IP mimics a real IP responding to ARPs. You will need to make sure that the IP used is routable to your network from the forward-facing device. Another option here is to use central NAT. Essentially, central NAT is a list of rules that say, when you do this, NAT like this. When networks get very complicated with hundreds of firewall policies, it can be very difficult to properly manage IP pools. By default, central NAT will be hidden in the GUI, but can be turned on. Central NAT is just a way of telling the firewall that you want to use specific NAT rules. This way, all you need to do is configure how you want your NAT behavior to work in the central NAT table. Then, when you enable central NAT on a firewall policy, it will look at the table in order to determine what needs to change about the packet. Back when we were talking about how packets are handled, I mentioned session helpers. Now we're going to go over what exactly a session helper does. Sometimes, certain traffic needs to be handled specially by the FortiGate. Additional actions will need to happen simply because of the kind of traffic it is. Also, there may be additional information in the packets that the firewall needs to know in order for the traffic to flow properly. As an example, we'll take an in-depth look at FTP traffic passing through a firewall policy that is NATing traffic. The FTP protocol can be simplified into three basic steps. Step 1 is the three-way TCP handshake. Step 2 is the login where you authenticate and set the mode. Step 3 is where data gets transferred. This can be getting directories, navigating directories, or downloading files. In Step 2, if the mode for the FTP connection is active, what happens is the client side sends the server IP and port information that it should transmit data to. Anytime there is a request for data, a new session is initiated from the server to the client on a random port determined by the client. When the mode is set to passive, the server tells the client what port it will send and receive data on. So, in this mode, the client initiates the data connection to the server on a random port determined by the server. This is a breakdown of an FTP connection. After the TCP handshake, the client machine sends the user credentials in order to log on. Once that's done, passive mode is specified and the server sends back connection information for the client. If we break this down, it sends back 6 numbers. The first 4 are the IP that the client machine should use for the data connection. The second 2 are for the port. In this example, the data command used is just a simple file listing. The server echoes back the connection information. You can see from here the IP listed is the WAN 1 IP. This is because the packets are NATed, so as far as the server is concerned, the IP that's connecting to it is 200.2.2.2. For passive mode FTP, a session helper may or may not be necessary in order for the traffic to flow. It depends on your configuration. Assuming that your policy allows all ports out, then there will be no problems. But assume for a second that your firewall policy only allows the standard port for FTP. Without a session helper to read the packet and find out that port information, there would be no way to allow the connection without allowing pretty much every possible port. Now we'll take a look at the same thing using active mode FTP. After login, the client sends the server the IP and port information it will need in order to transmit data to the client. Now the client is going to send its own IP, which obviously will not work over the internet, so when the FortiGate NATs this traffic, it needs to change that port command and replace the internal IP with the NATed IP. Also, since there's no direct way for the server to connect to the client, it needs to open a connection on the port so the data can be sent back through the firewall. After that, the communications comes from the server on the port specified by the last two numbers. If there is NAT on the policy, then changing the port command sent by the client is absolutely necessary in order for active FTP to work. Also, since there is NAT, being able to open the pinhole port for the data response to get back to the client. Traffic shaping can be used to provide prioritization of different kinds of traffic. It can also be used to rate limit based on the egress interface. Traffic shaping will be covered in more detail in the routing module. When a network gets overloaded and traffic is competing for bandwidth, traffic shaping is useful in order to make sure that the important traffic is still able to pass through. It can also be used to prevent a situation such as this by limiting high bandwidth devices so they do not consume unnecessary network resources. There are two different kinds of traffic shapers that can be configured. The first traffic shaper applies a total bandwidth to all traffic matching a policy, essentially sharing that limit with all devices passing through. So if you have a 500 kilobit per second limit on a policy that will be applied to your entire network, it would limit the total traffic allowed through that policy to 500 kilobits per second and drop the excess. The second applies the same amount of bandwidth to all IPs matching the firewall policy. In a shared scenario, it is possible for one device to claim all the possible bandwidth. In this scenario, you limit everyone to the same amount, but you need to be aware of the possible total. If each device in your network is limited to 25 kilobits per second, but you have 100 devices, that means that up to 2,500 kilobits per second is being allowed through the firewall policy. Guaranteed bandwidth is the minimum amount. The FortiGate unit will ensure it reserves that much bandwidth for the device. Maximum is straightforward and really doesn't require further explaining. With per IP shaping, be sure not to set guarantees for maximums higher than the bandwidth will actually allow for. Traffic shapers only apply to the traffic passing through them. They do not impose limits on traffic they do not touch. So if you had two policies and a traffic shaper on only one of them that had guaranteed bandwidth set up, the other policy has no traffic shaper, so it could consume all the bandwidth. If you are going to use traffic shapers, be sure to apply it to all of your traffic and set real guaranteed and maximum values, otherwise traffic shaping will end up being worthless. Within the policy, you can enable different types of security profiles depending on the kind of traffic the policy would be seeing. More detailed information will be provided about the individual UTM profile types in other modules specific to the individual UTM profiles. There is also an option called Client Reputation. By default, it is disabled in the GUI. What that does is fairly simple. Normally, when a UTM profile detects something, it does what it's been configured to, and that's the end of it. The event is allowed or blocked and logged accordingly. Client Reputation allows you an easy method of tracking who the problem users or devices are. You can configure what events you want to increase the reputation score and by how much. You can enable this feature on all FortiGate devices running 5.0. However, only devices with a local hard drive will have the option to view the reputation score. Without a hard drive, you will need to make use of a FortiAnalyzer or FortiManager, or make use of the FortiCloud service in order to view what the reputations are. Client reputation is a way to track problem behavior. Those users or devices that have a high reputation are behaving badly according to the rules you have configured and therefore need the most attention. By default, client reputation will look at data up to a week old and the score will be updated every 10 minutes. Client reputation is not a real-time monitoring system. Normally, the maximum number of monitored hosts is about 5,000. The actual number will depend on the amount of logs that get generated and the size you allow for the database. There are two options in the CLI that you can use to adjust the database size and length of time before rolling the data. If you adjust the window size to be larger than default, it means the FortiGate will consider older logs when calculating the overall score. This also means that the feature will take more CPU and memory, and that the score will be more accurate as there will be more data to look at. If you make it smaller, there will be less data, which could lead to making the scores less accurate. Changing the database size is also possible. A larger database obviously takes more storage space and requires more resources to maintain and can result in more hosts being trackable. Client reputation scores can be monitored by using the Threat History widget. In order to use this widget, the FortiGate needs to be a virtual machine or have a solid-state hard drive and not be a small home office model. Small home office devices have 2 digits in their model numbers, like a 60D or 90D. Medium business devices have 3 digits, and enterprise class devices have 4 digits in their model numbers. If your device can use that widget, then the other ways you can monitor the score are by using FortiCloud or FortiAnalyzer. You can also run periodic reports. The widget monitors the top scoring devices in your network. The widget can be configured with how many to track and even has settings for 3 variable time periods that you can select. By selecting different parts of the graph, you can drill down through it and find out exactly what was going on. There are also some CLI commands that can be used with client reputation. These are only available on devices where you can do local monitoring of the scores. We won't be discussing these in depth, but the commands are listed here and are fairly self-explanatory. As its name implies, proxy-based scanning uses a transparent proxy to deal with the communication. The proxy buffers the file for inspection during transmission. Obviously, this can cause a delay on files being sent since the entire file needs to be buffered or the oversize limit reached before the proxy will take any action. Once the file is completely buffered, the FortiGate will apply the UTM profiles to the data and take the configured action. This type of scanning can cause delays because no data is passed through the FortiGate unit until the proxy makes a decision on what to do with it. This means either the file is fully transmitted and scanned or the buffer gets full. Another option with some UTM profiles is flow-based inspection. Here, the files are scanned on a packet-by-packet basis. In this mode, There is no proxy involved, so you do not get the transmission delay that exists when using the file-based method. It has a higher throughput for data, but the disadvantage is that it is less accurate. The reason is how it actually functions, looking at the data in small chunks rather than waiting for the whole file. Each chunk is an individual piece that is not examined in relation to the others. Every protocol has a maximum file size for proxy-based inspection. If the file is larger than this limit, it cannot be fully inspected by the proxy, in which case you have the choice to block the file or allow it. The reason is pretty simple. Without being able to look at the entire file at once, proper identification and inspection is not possible, and it becomes a potential security risk. If a file is downloaded that is too large for the FortiGate unit to handle and has a pass action, no further inspection can be done on the proxy of any kind. This is why it is important to use a layered approach for things like virus scanning. Compressed files are also considered. The unit will attempt to decompress the file in order to subject it to whatever inspection options have been enabled. So if the decompressed file is too large, it will not be inspected, only passed or blocked. Just to compare the two methods of inspection side by side, you can see the pros and cons of using either one. Best practices say that you should always go for better security, which means proxy-based inspection is the better way to go. Flow-based inspection is there if you run into difficulties, but you have to remember that it is not as secure or accurate. Finally, not all of the security profiles can be switched back and forth between flow and proxy-based inspection. For example, application control and intrusion protection are only flow-based inspection, whereas a voice over IP profile is something that can only be done with a proxy. Another feature that can be enabled through the firewall policy is called Endpoint Control. The FortiGate unit will communicate with the FortiClient software installed on the PC in order to make sure that specific software is installed. This way, you can enforce that a particular AV software or other software is set up on a user's PC before allowing them access. The first part of turning on device identification is to enable the sniffing of traffic on the interface you want to do this for. The more interfaces you enable this on, the more CPU resources it's going to take in order to identify the traffic. The devices detected by the FortiGate are not static rules. The unit continuously monitors the traffic to see if patterns may change. You can never tell if a device changes its IP or not. If you forget to do this, when you create a device identification policy, you will receive a warning prompt. Device identification enables some of the detection options. Device user identification enables looking at the packets to try and find a user using that device. There are two methods for implementing device identification: agentless and agent-based. Agentless identification works by looking at the traffic patterns generated by the device, TCP fingerprinting, MAC address, and the HTTP user agent. In order for this method to work properly, it requires that nothing is in between the device and the FortiGate that will modify the packet. If there is, this will have a definite impact on the effectiveness. The other method is to do agent-based using FortiClient. Obviously, this is going to be more accurate as FortiClient can talk directly to the operating system, but is also limited due to this software not being available for every operating system. In the event that a device is being misidentified or you need to make an exception for a single user, you can set up a manual device entry in order to specify what the unit is. This way, when the traffic goes to the device identification policy, the entry is already entered and it will use the rules for that kind of device. Because you're making an override for a device, the only way to do this accurately is by specifying the MAC address. In order for the device identification to work best, the FortiGate needs to be as close as possible to the device generating the traffic. Proxies or natting will destroy any hope of accuracy. You can see the list of devices the FortiGate has learned by checking in the GUI under User and Devices, Device, Device Definitions. You can see in this example, test is a manually created entry. 192.168.1.1 is a router. .140 is a printer. .116 is a laptop. .222 is another router. There's even a transparent FortiGate virtual machine in the mix. Only the laptop has an operating system identified. This is expected. Routers and printers are not end-user devices, so there is no built-in entry for them. If you wanted to do that in your network, you would need to create a manual entry. You can also get this in the command line with the command diag user device list. There are three options when using a device identity policy. The first option is to simply try and identify all devices that are currently unknown. This sends you to a web page with an OK button. The idea behind the page is to be able to read the HTTP user agent information and attempt to identify the device based on that. The second option is to force FortiClient to be installed on all the devices that it can be handled on. If the device is identified as Windows or Mac, you can make sure the AV software has been installed. The final option is to attach an email to the device. Since you cannot do authentication in combination with device identification, this is a way of tracking whose device this belongs to. Here's an example of email collection being configured as a device option. In the first rule, any device that has an email that has been collected for it is allowed through. The second rule denies all devices. Down at the bottom, the option is enabled in order to make sure that the user of a device is presented with a web page to have them enter an email address. Those emails are not validated to make sure that they exist. By default, only the domain name is checked to make sure it is properly resolved. This is a look at the email captive portal page. It's a kind of user authentication, although the email is not confirmed with a reply. It is subjected to some validation checking. A valid email syntax is checked for and hostname resolution is performed. If your device has issues resolving DNS, you can disable the hostname resolution check for the email portals in the CLI. An object cannot be deleted if it is already in use. A VPN, address object, interface, etc. The GUI provides a simple way to find out where in the FortiGate's Unix configuration an object is being referenced. You can use the monitor section in order to determine how much traffic is passing through and on which firewall policies. The default is to list the policies by the active session count, but that can be changed. If you're going to be troubleshooting firewall policies, the first thing you need to understand is how the traffic is supposed to work. There are usually multiple firewall policies, so you need to be pretty sure which interface it is supposed to be coming in on and which one it should be going out on. Is there any kind of source or destination natting that should be taking place? It's also important to understand what behavior you're actually seeing. If it is a case of traffic being slow, a timeout, or an error of some kind. These are all very different behaviors, which means you need to be looking for very different things in the packets. You can use a packet capture from the command line in order to take a look at traffic and how it's moving around. You can also look at the output in Wireshark. To do this, you'll need to save the output to a file and use a Perl script that you can find on our knowledge base page. The format of the command is diag sniff packet, then specify the interface, followed by the filter, and then the sniffer level. The interface is the name of the logical interface. It doesn't need to be a physical one. If you're a super admin, you can specify the any interface. For debug levels, you can specify 1 to 6, which will affect the format of the sniff output. We'll go more into the levels shortly. If your device has internal storage, you can also do a packet capture from the GUI as well. The options in the GUI are exactly the same as those from the CLI, but it's a different layout. You specify a source interface and set up a filter. The real advantage of doing a capture from the GUI is that when you download the file, it is automatically converted into PCAP, a format Wireshark understands. This saves having to dump the output to a file and run the conversion Perl script. Creating proper filters are very important when you do a packet capture. No filter means it will look at all the traffic for that interface, which, unless you're in a test environment, is probably going to be a massive amount of extra traffic that you would need to sift through. The most commonly used filter options are to specify the host or network by source and or destination. Specifying the port and protocol for the traffic is another method of quickly and easily removing information from your packet capture. It's also common to use primitives in order to link more than one condition, like doing a capture for traffic from a particular IP, but specific to several different ports. Here are some examples of doing packet captures. The first one combines capturing traffic from a particular IP address and protocol. It's important to remember what is going to happen with that traffic, like if it will have NAT applied. If you don't set up your capture correctly, you will only see outbound traffic and not the reply. The second example shows a packet capture for FTP traffic. Now, FTP operates on two separate ports, the initial port, which is normally 21, and then a random port. So if you wanted to see everything that happened, you would need to look at all traffic on two separate ports with the same host. As a final example, we have a packet capture of traffic performed on traffic coming from a device logging into the FortiGate. For something like this, you would need to make sure you somehow excluded the administrative traffic from the packet capture. If you're capturing from the CLI, what level should you use? The options are 1 to 6, which was mentioned a little bit earlier. Level 4 is the most human-readable output. For converting to Wireshark, you can use either 3 or 6. There is no difference in terms of what gets converted. Sometimes you want to get a look at the decision-making process. To do this, you need to use the command diag debug flow. It's more of an advanced command and requires several steps to set up properly. The first step is optional. It enables the inclusion or exclusion of the function name in the diagnostic command. The second step is the important one. This is where you set up the filter for the diagnostic. It's the same idea as a packet capture where you set up a filter. The difference is that each option is a separate command. So if you wanted to filter on a specific IP and a specific port, you would issue two separate commands. Next, you specify that the diagnostic should start and continue for a specific number of packets. Finally, in order to see any diagnostic output, you need to enable debug mode before you can see any output. This is an example of setting up a diag debug flow command. The first line states that the debug output will include details on the function the FortiGate called in order to execute the action. Second, an IP address was specified. Just like a packet capture, you could limit this to a source or destination. ADDR applies to both source and destination, so this way it will apply to traffic to or from 4.2.2.2, which should be the outbound traffic as well as whatever reply comes back. Next, protocol 1 is specified, which is ICMP. According to this debug, it will look at any ICMP traffic to or from 4.2.2.2. Then the debug is started and will continue for the next 10 packets, and debug mode is enabled. In total, 5 commands need to be entered separately. Here are some sample outputs from a packet capture. You can see that with level 4, the port is specified as well as the packet's direction, in or out. The packet is also categorized. With this capture, we can see a ping from 192.168.100.110 to 4.2.2.2 on the LAN port. We can then see that packet sent out the DMZ port with a different source, which means the firewall policy natted it. We then see a reply coming back on the DMZ port and getting sent out the LAN back to the original sender. If you needed to take a closer look at the packet contents, you can set a level 6 capture, which you can see contains the actual packet contents. Compared to a packet capture, take a look at the output of a diag debug flow. The following is the output for a single packet. The first thing is that the root VDOM received a packet. It was protocol 1, therefore ICMP, and the source IP was 192.168.100.110, with the packet being destined for 4.2.2.2. Finally, the packet was received on the LAN interface. The first thing the FortiGate does is allocate a new session. This also tells us that it is not traffic that the FortiGate has recently seen. It's then time for some routing decisions. The interface is hashed and a route is found to the destination using the gateway 192.168.3.1, leaving on the DMZ interface. Next, we can see the traffic is allowed by Firewall Policy ID 1 with source NAT enabled. The packet is source natted to 192.168.3.99 and the source port becomes 62,464. If this traffic was getting destination natted, the debug would specify DNAT. The packet gets sent to IPS because that firewall policy has a security profile enabled. We can't see the packet details, that's what a packet capture is for. However, this debug will show you all of the decisions that go into passing traffic through the FortiGate, so it's important to make sure the filter is properly set up to remove as much excess information as possible. Now it's time for the lab exercises. The first lab is all about working with firewall policies. Exercise 1 goes into creating different objects and putting them into rules. Exercise 2 has you working with different policy actions. Exercise 3 will have you make a virtual IP. In Exercise 4, you will work with IP pools. Lab 2 is optional and covers traffic logging. In Lab 3, you will be working with device policies. If you finish the first lab, go ahead and move on to Lab 2 and Lab 3.